Hi Martin, thank you very much for your visit here in Künzelsau for the CADFEM conference and your great presentation. Can you give us a brief summary about your presentation?
Sure. So Markus, thank you for the invitation, and I give a short summary of my presentation. So my presentation was about PyAnsys Heart, and PyAnsys Heart sort of fits in the larger ecosystem of Python libraries that we have within PyAnsys. So usually these other Python libraries, they actually expose certain features of the products. And what we actually did is build a layer on top of that to enable domain-specific simulation workflows. And in this case, cardiac simulation workflows. So we build on top of the original PyAnsys core libraries.
Okay. And why is there a need for a different layer, I would say, on libraries? So what kind of libraries did you use here?
Right, so there is a need because these simulations are very complex, right? So you need a lot of domain-specific knowledge, not just on the mathematical concepts, but also on the physiology and pathophysiology. So these simulations are too complex for sort of single users to actually use properly. So instead what we did is we tried to consolidate a lot of the best practices that are relevant for these simulation workflows into a single library, so that essentially the user can cherry pick the relevant components from that single library.
Okay, so that sounds that the user should not, but can be an expert in this area?
Yeah, so in the end, everything that we do is just a sort of Python layer on top, but it doesn't mean that you cannot see the details, right? You can still see whatever is happening behind the scenes, even on the solver level. So whatever input we give to the solver, that's still sort of transparent, but in a way for the non-expert user, it does not have to go into that much detail. In order to make these simulations work.
Okay, what does the user see when it comes to the libraries?
With respect to the Python code, essentially the user sees, of course, the documentation where we provide a lot of examples on how to define these simulation workflows, and then you essentially have a Python environment, so you would need to have some basic knowledge on Python, so that's some scripting, but in the examples we show how you can consume the different parts of the library to set up your workflow. And we give end-to-end examples, so in the end also with the example that we give, you get a simulation model where you can appreciate what we can essentially do and how much control you would have.
And what is the industry you are looking for that solution?
Right, so we have essentially three sort of fields that are of interest. So we have the medical device industry and the pharma industry, so that's sort of the industry part of things. Then we have academia and also clinical practice. And for the industry, it can be medical device industry or pharma, where for medical device we want to know how an implant behaves, for instance in an actual heart, so in a virtual heart. Because of course these kind of experiments are very costly if you would do them on an actual patient, or even unethical, right? So you don't want to necessarily, have a single subject that you do all sort of things to. You want to have a virtual model where you can do things that you would otherwise not be able to do, and measure things that you would otherwise not be able to measure. So that's one, and then there is the pharma, essentially, where also the effects of drug on the organ level can be modeled, through this Python library. And then for academia, it's interesting on a fundamental level, fundamental understanding of how the heart works and how the heart works in the wider system, but also for education and training, right? So not just engineering students, but also, for instance, medical students that will also have to learn to work with these tools eventually, because in the future, when they are actually practicing medicine in real life, they will also be exposed to some kind of simulation tools, hopefully, probably. So it's in order to train them, this library can also be used to sort of study different pathologies without them having to know the deep fundamentals of simulations. the very specific details that come with simulations, like your solver settings, etc., contact, this kind of stuff. The things that we spend hours on, they shouldn't have to spend.
When it comes to cardiac simulations, like biomedical simulations, I think it's from the physics side very complex, and you need a lot of knowledge for model preparation, meshing, the simulation itself, the post-processing. How do you overcome these kind of problems?
So in the end, in our library, we consolidate a lot of the existing knowledge in literature, right? So when you go to academic literature and all the different groups that develop these types of models, there is a lot of different tools being used, and we try to apply those methods in our library using our simulation tools. So in a way, we did the translation for the user, and we also, played around a lot with these models to try and understand what works, what not. If it should be an explicit, if it should be an implicit, what coupling do we need, etc., and how do we couple, both on the deep material model level, but also on sort of the system level. How do we do that? Do that coupling.
So there's a lot of pre-work already done and a lot of best practices implemented in this solution.
So that was a lot of work, right? So I mean, it's something that we're quite proud of, that we were able to expose in a relatively simple way such a complex thing. Organ.
Okay, understand. For me as a user, what kind of background should I have to use this tool?
So in its current form, right? So in its sort of core library form as it is now, any engineering background would do. Even some dedicated medical students could actually dig into that, especially those that are more interested in sort of data processing. Because in the end, we provide full examples. And we essentially are within a Python ecosystem. So there's a lot of different Python libraries out there that are already very well documented. And some of those we use. And there's a lot of examples on those other libraries as well. And we sort of have that same structure in place to have the examples so that you can learn from those to understand how it sort of fits together, etc.
Okay, great. Okay, so sounds like a really proper solution here. How can I use it? Is it free, or how can I get it?
Right. So this is published under the PyAnsys initiative. So PyAnsys in itself is open source. So this is published under an MIT license. All of the individual libraries, our library as well. And the only thing you need is a few core Ansys products that are licensed. Right, but the layer on top is unlicensed, and you can freely use that and modify that in whatever way you would like.
So when we look more in technical details, what kind of products do you use to bring all this together? The preparation, the modeling, the meshing, the simulation itself. What is under the hood here?
Right. So. Indeed, if you look below our Python layer, then in the end you will see our flagship products like Fluent. We use it for meshing, sort of unconventional choice, but that's the beauty of PyAnsys. You can choose whatever tool you would like. So we use Fluent for meshing due to its certain characteristics that are useful for us, or certain features that are useful for us.
And I think also a very robust way.
A very robust way for meshing, so that's very convenient for our applications where we have relatively dirty meshes that we need to do some cleanup, but we don't want to do manual cleanup. We want to automate as much as we can, so that's where Fluent is really helpful. Then we have LS-Dyna, and we use that as our core fitted element tool, let's say, and we retrieve data, or we interact with LS-Dyna through PyDyna. So that's the Python or the PyAnsys library that is associated to LS-Dyna. And then we read results with DPF through PyDPF. So that's again the PyAnsys.
What is DPF?
So that's a data processing framework, and there we essentially consolidate a lot of the data readers, because each of the solvers has different data formats. With DPF, we can read most of those formats into a sort of Python environment. And for the Python environment, we strongly rely on PyVista and VTK for all of the data handling and parts of the visualization. So that's where VTK is really helpful. Also, if you want to visualize on a web interface, for instance, VTK has some ways to do that relatively easily, where a script that works locally also works remotely in a web environment.
Sounds like a lot of tools, but what I understand is, okay, when I use PyAnsys Heart, I'm not looking into these libraries in detail. I have just one library here where I can then use for doing the simulation, for example.
And on top of that, what we have also as part of the examples, we can process a lot of public data that's already out there. So even if you do not have data, you can build simulation models. Because one of the bottlenecks for a lot of these companies or users is that they don't have any imaging data of patients, right? Because that's always very sort of protected in a hospital environment due to obvious reasons. So we essentially have also a way to consume that public data, public segmentation, so you can get a cohort of patients relatively easily.
Okay, when it comes to post-processing and animations, so they're really impressive animations, seeing the heart pumping, something like that. How do you do this?
So, as I mentioned, we use VTK, right? Sort of as the visualization toolkit. VTK stands for visualization toolkit. So we bring all that data to that format, and we use that for visualization, also some post-processing, because it has some very convenient methods already implemented. So again, in this Python library that's freely available from the wider Python ecosystem, that already exposes a lot of useful methods for visualization. So that's something that we rely on quite a lot. Now we can also do more advanced animations, right? So VTK is useful, but mostly if you have static data. If it's more dynamic, then of course we could also look at platforms like Omniverse to help us with the visualization of the data. But not just visualization, right? It's also integration of multiple data streams into a single development platform. So I see some potential there to actually build very nice, slick-looking applications in that environment, which is very developer-friendly, I would say, both in terms of visualization, but also in data integration, or even bringing in AI models to help you with certain parts of the process.
Yeah, I think NVIDIA Omniverse is a real big platform to democratize simulation, to visualize, of course, and to, as you said, to bring AI into it. Are there plans, further plans to do more on Omniverse at Ansys?
So we do have some projects, but to be honest, you will probably see those in the coming months or years. You know, when we start to work more on the actual applications and that we have some proper integration into this platform. It's a bit early to really make a proper statement with respect to Omniverse in that sense.
But there will be some.
There are some ideas, and well, let's just keep it at that teaser.
Something is coming. Okay, great. Where do you see the future of PyAnsys and PyAnsys Heart?
I think that the current engineers are still very locked into their specific tools. So I think PyAnsys sort of unlocks a lot of potential in using these tools with other sort of less conventional workflows, where actually you're only limited by your own imagination, because you may have some experimental data, you may have some other measurement data that comes, for instance, in our case, from patients, and you want to sort of bring that together with your simulation model. You need a common environment that handles that interface. And for us, that would be the PyAnsys libraries, or the Python in general, right? And that's how developers can bring all of this together, either within a sort of vanilla Python environment, or within, for instance, Omniverse, which also allows some Python integration. So it will develop further and further, Yep.
There are many plans, and we will see something in the future.
Yes, hopefully a lot in
Okay.
the future. Yep.
Okay, great. So thank you very much, Martin, for your time.
Yep. Thank you for the great questions, and thank you for this great conference. It was really inspiring.
Thank you.
Thank you.